Yeah, welcome everybody to the last quantum seminar in this year. At the beginning, let me briefly introduce to you our speaker. It's our great pleasure to welcome Professor Markus Arndt from the University of Vienna. Markus Arndt studied physics at the University of Bonn and then later on at the Ludwig-Maximilians University in Munich. And where he carried out his PhD work there in the group of Theodor Hensch. And then he got his degree in 1995. And then he worked for several years as a postdoc. First, he got the Theodore Lane and DFG Fellowship at the École Normale Supérieure de Paris. And then followed by postdoc 2 years at the University of Innsbruck. And then from 1999 until 2002, he got an assistant position at the Institute for Experimental Physics at the University of Vienna, where he conducted, for instance, diffraction and interferometry experiments on fullerenes. Which then culminated in habilitation about atomic and molecular interferometry. Professor Arndt, he was then appointed extraordinary professor at the University of Vienna in 2002, and then 2 years later as a full professor in quantum nanophysics at the same university. He got several prizes. I don't want to list or to mention all of them, but just to stick to a few of them. In 2000, he got the Erich Schmidt Prize of the Austrian Academy of Sciences and the Fritz Kohlrausch Prize of the Austrian Physical Society. And in 2012, he got the ERC Advanced Grant of the European Union. And then only recently, in 2019, he got the Robert Richard Pohl Prize of the DPG, so Deutsche Physikalische Gesellschaft. We are happy to have you here, Professor Arndt, as a speaker for today's quantum seminar. And we are looking forward to your talk about the long road towards interferometric tests of non-standard physics. Professor Arndt, please.
Thank you very much. So Mustafa and Arne for organizing this seminar and for having me here. It's a great pleasure. And I will share my screen in a minute. Voilà. Okay, this you should see, huh? Hopefully. Yeah, and it's about interferometry, matter wave interferometry with big things. I tend to call this universal matter wave interferometry because we try to do this kind of wave particle trick with essentially everything that we can get our hands on. Atoms, molecules, nanoparticles, biomolecules, as you will see. And this has various motivations. One was and is just curiosity. In particular, when we started that, still with Anton Seiling in 1999. So that's also why it's called the long road, because it's really 20 years by now that we've been doing this in various different configurations and with various particles, with various goals in mind. And curiosity is one of them. And then there was always the question, so, well, if you can do if you can see the wave particle duality of atoms, electrons, neutrons, small molecules, how far can you go? And what can be potential and fundamental obstacles? And that's where non-standard physics may come in the end. I cannot report on any non-standard physics. Up to now, everything is perfectly quantum, perfectly established. And nevertheless, when we try to publish things in this field, we typically, in 50% of the time, get criticism that this would be fundamentally impossible what we're doing, which is kind of strange because it's quantum mechanics. But so I understand that there are also chemists here in this audience, partially. And in particular, with the chemistry journals, we sometimes have to fight because they kind of, even though there's electron delocalization easily accepted by everybody, also in chemistry, the full delocalization of an entire molecule sometimes seems to cause puzzlement. And in a certain sense, it should. And we will have a look at what we're doing there. So yeah, as always, of course, what we're doing is teamwork. The teams change over the years, and some of the people on that list, I think you have seen in the seminar already, like Philipp Haslinger here and James Millen, who were members of my group. Philipp was working on the ultimate interferometer and James Millen on cooling of nanoparticles. And so it's a perpetually changing mix of people, very dedicated people, and sometimes even climbing up to our mountains here. We need a lot of collaboration with theorists, with chemists, with people in nanofabrication and in theory, and also they are listed here. To read everybody's name, and to mention individual contributions would take the rest of the talk, but it's documented here, so they're all important. And now only the clicker, okay. So somehow what we're doing is kind of, sometimes I tend to say trivial. On the other hand, it's not, but it's something that is very well established. And we are approaching the centenary of Louis de Broglie's invention, if you wish, of matter wave duality in 1923. So it's pretty close to 100 years. And very early on, essentially in the same year, people tried to see this. And if you read Otto Stern's papers, they also tried this very early, managed in the end in 1930 to see something, but even before Davison and Germer actually got the electron diffraction accidentally to work, Stern was already working on that. And so, as you know from textbook physics, it works. You see matter wave behavior, the de Broglie waves for electrons, for neutrons, for small atoms and small molecules. That has been a very old story in the 1930s. And then it took quite a while, up to the 1980s, 90s, to really start atom interferometry as we know it today, which is becoming an increasingly successful domain of research, also part of the European flagship, quantum technologies, because atom interferometry is extremely sensitive in accelerometry for geodesy, gravitation measurements, and things like that. The start of this field was kind of accompanied and then temporarily moved entirely over to the then entirely new field of Bose-Einstein condensation, which is also about matter waves essentially, but where the interference character was less in the focus. Most people then went into solid state simulations and things like that. But as you know, there are hundreds of groups now literally working on ultra-cold atoms with Bose-Einstein condensates, Fermi gases, where you can see matter wave effects very clearly for very huge ensembles between 1,000 and 1 billion or so atoms in one ensemble at ultra-low temperatures, typically anywhere between, well, picokelvin is really the extreme, up to microkelvin. And I emphasize this because, well, this is an established field. Matter wave physics is really an established field. And there shouldn't be any doubt that this really works. But here with these Bose-Einstein condensates, it's really interference of individual atoms. So the de Broglie wavelength that plays a role there is typically of the order of even up to a micrometer if you get to the recoil limit, so 200 nanokelvin for cesium or so. So these are very long wavelength, very cold, very weakly bound ensembles, huge ensembles of atoms. Extremely interesting, but for this specific talk, it's not at the focus what we're doing. So we started actually here in Vienna then, with preparation already in Innsbruck, but then in Vienna in 1999 with fullerenes, C60, C70, and since then have been fighting really our way through to various different particles, from organic molecules over vitamins, as you will see briefly, big macromolecules composed of about 2,000 atoms, antibiotic polypeptides, neurotransmitters, and whatsoever that you can delocalize and where you can see quantum interference effects. And of course, the question is, how far can you take this? Does it make any sense? And is it possible? And what do you expect to see if you go to 10 to the 7 atomic mass units, or 10 to the 9, or 10 to the 10? And you may have heard that people also were speculating what would happen if you could see quantum gravity at 10 to the 14, or the quantum nature of gravity at 10 to the 14 mass units. This is very far out. But still, so the question is this fundamentally conceptually possible, or is there an intrinsic limitation given by some kind of physics? And you will see there's a whole list of things that can come in at a certain mass range that may modify quantum mechanics somehow, or may modify the observation possibilities. What I would just like to emphasize here in this case, it's really in an extreme complementary regime to this ultra-cold domain. The number of atoms in the end will be similar. Currently, actually, our record molecule is roughly 2,000 atoms per molecule, which in some Bose-Einstein condensate experiments you also would use. And the goal really is to get also to a few million or so atoms. But the de Broglie wavelength in this case is always extremely tiny, because here we're talking about covalently bound or van der Waals bound, depends on the particle, molecules or particles which act really as one. And the de Broglie wavelengths, the shortest we had so far, were of the order of 30 femtometers or so. So that's really the extreme, 30 femtometers against micrometers or so. So many orders of magnitude in between. And accordingly, the technologies also need to be different. Conceptually similar, but in practice, pretty different. And so why would you want to do that in the first place? As mentioned, for curiosity, can we do it? Is there any change if we modify the internal structure, if we modify the shape, if we modify the mass, complexity? And nowadays, in hindsight, so to say, it sounds almost trivial that this should work. But before we started, people were wondering whether even for fullerenes, which are round structures and ball-like structures, people were wondering what the role of vibrations and rotations would be, and if that wouldn't carry which path information, or whether decoherence would outrun the entire effect. And we've kind of always walked the tightrope, the line between coherence and decoherence. The particle that you see at the lower bottom part, which is kind of our record holder at the moment, is really hot, internally hot, something like, it's not even exactly known, but currently the suspicion is it's about 900 Kelvin or 1000. So it's extremely hot internally and survives that also for the short flight time. So it will emit vibrational photons, but in a long wavelength range and things like that. So there's coupling to the environment, but in a way that is not yet disturbing the quantum behavior. So it is a complex thing, and it will not become easier for larger and larger particles. So that is something we need to be aware of. So, but the question is to understand the transition from small to big, low complexity to high complexity, and whether we can learn something about physics. So that's this universal matter wave interferometry, and it's not non-classical but non-classical states of mesoscopic systems, essentially Schrodinger Cat states, as you will see, or macroscopic superposition states. And then there's the open question, and that's really an entirely open question. I don't have a good answer for that. Can there be any new physics, and would we be able to see this? Since the new physics is so ill-defined, we will briefly talk about dark matter in the end. There are experts in Mainz who know how vast the range of predictions is, what you would be able to expect under what circumstances, so to say. So it's very hard to predict how sensitive this would really be in the end. And I would be happy to discuss, maybe not here in this hour, but later with experts in Mainz, what we can do there. But one of the reasons why new physics can be probed is that all these matter wave interferometers are extremely sensitive force sensors, and there's a number of effects that scale favorably with mass, typically with mass squared. So if you increase the mass by a factor of 10, you get more sensitive, at least by a factor 100, to some sorts of effects. And that is a good thing, and that's what we're trying to exploit. On the other hand, there are also particles which are not at all spherical, like this little silicon nanopencil on the right-hand side, with which we haven't done interference yet, but which we also try to launch and control. Probably James Millen talked about that when he was here. So you can also use this as rotation sensors. just to understand the concepts, we start very elementary, just in a slide. Kind of textbook-like experiment. What you now literally find in textbooks is this kind of experiment where we looked into the simple far-field diffraction of, in this case, phthalocyanine. We've done this with fullerenes, with phthalocyanines, with the ciprofloxacin, which is a typical drug that you would take as an antibiotic. So you can do that with a variety of things. Actually, you cannot do the antibiotic diffraction at these gratings. You need to use light gratings, as you will see. But anyway, so the question is how, for all these experiments, you need a launch pad, you need free flight, you need a diffraction element and a detector. And for the next generation of experiments that you will see, you need an entire interferometer, or a variety of interferometers. And the choice of the molecule here is only for ease of detection. Phthalocyanine is a very efficient dye, which if you land it on a glass slide in vacuum, you can image it in single molecule fluorescence, even with 10 nanometer position resolution. So it's easy to detect. And you can launch them from a glass slide on the left hand side. Here with my mouse is moving there. Let's see if I can get a Zeigoption laser pointer. Yes. So the molecules are coated on that slide, and a diode laser, simple diode laser, is focused to a micron or so to evaporate the molecules here. And then Heisenberg's uncertainty tells you that if the position, the location of the evaporation is extremely well defined, then the momentum is not. And this means that there's a transverse uncertainty of where the molecule wants to go, a quantum uncertainty. So that generates transverse coherence, and that is of the order of several slit separations, which in this case were 100 nanometers separated, as you can see in this electron micrograph. And so you can imagine that this molecule is delocalized over several of these slits at the same time. The wave function of this molecule is delocalized. And because of that, you expect and you see interference. So if the molecule lands on the quartz slide, there's a certain chance to find it here or there, and the probability distribution is exactly what you expect from matter wave interference. And this is what you find really in the fluorescence microscope that is built to image this this ensemble of molecules that landed here on the quartz slide. And because they fly with different velocities, the slow ones take a little bit longer and fall deeper in the gravitational field, and because they have more time, also the interference pattern spreads out further, whereas the faster ones here on top, which haven't fallen so far, they're still further together. So that's the, in principle, simple idea. The question is, can we now just take that idea and extrapolate that to, say, a bacterium? And the answer is no, at least not with any technique that we know, and not on Earth, because you need to have extremely long de Broglie wavelength to do this. And well, actually the bacterium would not even fit through this grating, which has only 15 nanometer openings. And I mentioned briefly that even ciprofloxacin, which is a standard small molecule, that this wouldn't diffract in such a grating. And that is, the reason for that is that it has an electric dipole moment. And the electric dipole moment, depending on its orientation when it's flying through the grating, it is highly excited. It rotates typically at 10 to the 10 times per second. So it will have, different molecules will have different orientations when they fly through this grating, and with local electrical charges, which you can never avoid in these gratings. They get tiny deflections, and that destroys the interference pattern. We've studied that a bit in detail. I won't show this here. But so the key message is, if you want to work on something that has potentially a dipole moment, go for light gratings. At least not material gratings with van der Waals forces, Casimir-Polder forces. And so that's also what we did. And the other question is, well, can you go on with this far-field diffraction like you know it from textbooks? And the answer is, well, if you get extremely cold and without gravity, yes. But if you have realistic sources with a flux that is serious, so to say, not only a single particle, then they will, at least up to now, not yet be very cold. And in the gravitational field, they will accelerate anyway. And so it's much easier to work with near-field interferometry techniques instead of this simple grating diffraction. And that is why we built already quite a while ago what we call the Kapitsa-Dirac-Talbot-Lau interferometer, and later, based on that, the long baseline universal matter wave interferometer, LUMI 1.0. So this is targeted at higher mass, not yet the highest mass, but conceptually that should reach also to 1 million. We haven't done this yet. Currently, we're at 25,000. So the concept of this interferometer, I'm not sure if this will be work. Oh, there's music. How do I? Sure, if I can switch that off. Huh?
I don't hear anything. I mean, like,
that's good. Yeah. Then, if you don't hear the music, then I just pull out my earplugs for the moment. And so this is a 3 grating interferometer, where the first grating prepares coherence, the second grating does the diffraction, and the third grating is for probing the interference pattern. And the essential part is the central grating, the light grating, which is a standing light wave of 532 nanometers. So it makes a 266 nanometer grating period. And this works on the molecules via the dipole force. So the electric field of the laser acts on the polarizability of the molecule, induces a dipole moment. The dipole moment reacts to the electric field. That makes an energy times time divided by h bar. That's a phase. And well, this is now just moving on. There's one of these molecules. We did that with a variety of molecules, but the concept is always the same. So you evaporate them, in this case, evaporate the molecules, send them through the first grating where they are delocalized. And oops, a minute. I just have to stop it somewhere where you can see. All right. So the molecules come out, hit the first grating, and the magic, if you wish, happens really already in the first grating. Because there again, you have tiny slits, which are here 110 nanometers wide, and they delocalize the particle such that the wave function fans out sufficiently that you overlap several nodes and antinodes in the standing light wave, which imprints the phase, so you get the spatial modulation of the wave function, and that evolves into an interference pattern that you can probe with the third grating. And so that's happening here. And then the particles are detected by some sort of mass spectrometer. At the moment, in these experiments, this was still a quadrupole mass spectrometer, which is surprisingly universally applicable. Sometimes we use time-of-flight mass spectrometry, sometimes fluorescence imaging or other techniques. But what you expect to see and what you see in the end, there's still the music here, is is an interference pattern which now looks like a sine wave. And the visibility of that sine wave, that's kind of the indication of how quantum the effect really is. You have to be sure, and you have to make sure that you distinguish this clearly from a classical moiré pattern. Even with a standing light wave, there would be a kind of moiré pattern, a shadow pattern, or at least classical trajectories would also be deflected to form a pattern, and you have to make sure that you distinguish this clearly from a quantum pattern, and we will do this. But so we've acted with this interferometer on a variety of things, and just to mention, with 4 different vitamins, antidepressants, and antibiotics, for the sake of metrology, I should say. And I come back to that in a minute. It looks as if it didn't have anything to do with dark matter, but it has, because it's the same technique that we use and the same deflectometry that we would use also to search for dark matter. But so you can apply this to a variety of things. Essentially everything that flies and that you can detect also interferes. At least still in temperature range, which is pretty classical somehow. All these proteins, all these vitamins were heated to 500 Kelvin or so. So it's not at all cold. And then we took the same interferometer concept, but stretched it by a factor of 10. And the purpose for that was to be able to increase the mass to become more sensitive to effects from the outside. And all this is on the road to more and more massive things that should in the end also allow us to test non-standard physics. So this instrument has a 2-meter baseline compared to atom interferometers or record atom interferometers like Stanford, Mark Keswich's experiment, which has 10 meters. That's still a factor of 5 smaller. but we're in an entirely different mass regime and testing different things. The idea is still the same. The first grating mounted here is a nanomechanical grating. The second one is a light grating. The third one is again a nanomechanical grating. The first one to prepare coherence, the second one to do the diffraction, the third one to probe the interference pattern. Because it's so long and sensitive, it has to be mounted with extreme care in terms of vibration isolation. This is sitting on a 160 kilogram Minbar bar with suspension from a pendulum and Teflon balls and stacks actually of Teflon balls and steel bars, eddy current brakes. So everything extremely well isolated so that this thing doesn't move by more than 2-3 nanometers typically. And that is critical because the anti-interference pattern is only 266 nanometers and you want to maintain a high contrast. In particular, later, if you want really to do metrology and search for things that you don't expect, so unknown physics, then the contrast has to be stable. And here currently it is stable within 1% roughly. And we've applied this interferometer now for a variety of things. Atoms like cesium, barium, strontium for various magnetic measurements that I will not be talking about. We had C60, C70, anthracene, and adamantine 10, and that was for magnetic measurements. We looked at tripeptides like alanine, tryptophan, alanine, and the macromolecule that we will see in a minute. And so the instrument can handle really short de Broglie wavelengths, currently already 50 femtometers. So that should be good for masses up to 100,000 mass units if you can produce a source of 30 meters per second, which for atom interferometry is fast. Huh? A so-called LVIS source, low velocity source in atomic physics, that would naturally come with 30 meters per second. Here we have to play with tricks, and so far we didn't. Huh? But already then, in the current setting, this is sensitive to forces of the order of 10 to the minus 26 Newton. And so our kind of record holder at the moment is a perfluoroalkyl functionalized oligoporphyrin. So the chemists will allow me that I don't explain the details of that molecule, but the trick of this, this fluorinated molecule is that this fluorine shell helps that we can get it into the gas phase. It reduces the polarizability per mass. We also suspect that it makes a kind of, because of this strong electronegativity, that, that the charges are favorably distributed like a negative outside shell. At least they're relatively weakly bound. We've seen that in many cases of similar molecules, that the evaporation is much easier for these molecules if you perfluorinate them. Like, it's a bit like coating them with a Teflon shell. It's not exactly the same thing, but a similar concept. And so our friends in Basel synthesized these molecules, Marcel Meyer and Patrick Zwick. And they could go up to roughly 2,000 atoms per molecule. And it's, as they call it, a family or a library of molecules. And that is an interesting thing, because when we started our experiments with fullerenes a long time ago, people already wondered what would happen if you have a C13 instead of C12. If you're able to distinguish the molecules, is that a problem? And of course it's not, because we're always talking about single molecule interference. It's always a single molecule interfering with itself. And you only have to make sure that all these particles are sufficiently similar in velocity and interaction with the environment, that they create the same interference pattern. And in that specific experiment, I typically tend to claim that in this single run of that experiment, we have done interference with more particles than anyone in this universe has ever done together, so to say. And the reason for that is, so of course there had been experiments with lithium, with sodium, with rubidium, with cesium, essentially with the entire potassium, of course, the entire alkali, Rho and occalum, and then with all noble gases and with the different isotopes of all the different atoms. But here, the interesting part is that there are literally billions of structural isomers, because it's not a complete molecule, so to say. So it has 60 saturation bonds, but only 56 or 57 are typically really filled. So there are enormous amounts of possible configurations that are slightly different, and also of how the arms can be shaped and twisted. That is different. And of course, the internal structure or the internal excitations, these are really hot molecules, a few hundred Kelvin hot. And so they can be they are in vibrational states, highly excited rotational states, hyperfine states mixed, Zeeman states mixed, everything mixed. Huh? So internally, it's really like a classical body, but externally, and we're only looking at the center of mass motion, and it can still decouple from, so internal and external motion can still decouple. And that's kind of a lucky coincidence. If you heated that molecule by a factor of 2, only a factor of 2 more, I suspect, we haven't done this, we were not able to do this, but my suspicion is if you heat it by a factor of 2, you wouldn't see anything. And so in this specific case, there are 25,000 mass units, between 1,800 and 2,000 atoms per molecule. So really like a small condensate, but here really covalently bound. A variety of different funny atoms in there, like fluorine and sulfur and zinc. And it's traveling at a speed of an airliner. That's like an Airbus 320 when you're flying from Vienna to Mainz, to Frankfurt. This is typically about that speed. So it's really fast. And the diameter is big, 5 nanometers, and the de Broglie wavelength accordingly very small. And the nice thing, and kind of surprising, and at the same time not surprising because it's only quantum mechanics, you see a nice interference pattern. Now, if, as mentioned before, we have to make sure that this
Markus,
yeah?
What means normalized there?
Oops. That this is not a single count, so to say.
And where's the baseline?
Okay, let's see. So this is probably really the baseline here in that experiment. Probably is still 0. I have to remember now. Of course, there is an offset. So to be honest, for that particular curve, I don't remember the baseline exactly. I will show you nevertheless just in the next slide, and then it becomes clearer. So what you want to extract, the number that you want to extract, what you're referring to, so to say, is what is the visibility. And here it looks like a moderate visibility because it has, say, 0.3 on 1. So that would be, if it were a half, it would be 30%. So it's here, this curve is roughly 20%. If you really think that 0 is the proper baseline, which is not shown here. So, but if you, and I think that is what we did. So if the 0 is the real 0, then there's a fringe visibility, and yeah, roughly judged now from looking at that 20%. So, but that's not the maximal fringe contrast curve. Well, it doesn't go much higher here. 28, 26%, but roughly. And of course, in this electron, in this quadrupole mass spectrometer with electron impact, there's always some background. Since the original data are now 18 months old, I can't remember the count rates exactly. But well, the total counts of the order of hundreds per second, so to say. And the dark counts had to be subtracted first. And even then there's some noise level still that is a bit hard to eliminate. But the important point nevertheless is that if you look at the fringe visibility as a function of something that should depend on the matter wave nature, so you could vary either the velocity, or you can change, in this case, the power of the middle grating, of the light wave grating. So that changes the dipole force, the phase shift in the middle grating. And as a function of that, you expect a certain change and variation in the fringe visibility. That's easy to calculate. And you can compare it to the assumption of classical billiard balls coming in following Boltzmann distribution, but also being deflected by the same light field. You would also, for a classical ball, you would also expect classical dipole forces. So without delocalization, you would also see a Moiré pattern, but the contrast of that would be shifted to a different power by an amount which is substantial. And so the red line is kind of the classical phase-based prediction. and the blue line is the full quantum model. And the nice thing is that you can really use the same Wigner formalism that was originally developed for our purposes by Klaus Hornberger and Stefan Nimrichter. You can relatively simply exchange the classical and the quantum formalism in the same concept, so to say. And yeah, here there's a relatively high contrast, and that's kind of surprising and nice. Voila. So what do we learn from that? First, that quantum mechanics is okay, which is good. That's also a good message for anybody working in quantum information technology, because if it kind of broke down at a certain point, it could be a problem. But we can also test, at least get to the edges of reasonable tests of alternatives to quantum mechanics, and that is something that I want to briefly elaborate on. Many of you may have heard that there are different interpretations of why our world is classical, or appears classical. Maybe it's not. Maybe everything is quantum and that's it. And of course, the one very fundamental reason why our world appears classical is because of decoherence, because things couple to the environment and all your quantumness gets entangled with the environment and effectively so dilute that you don't see it in the individual system. So that is definitely a thing that is valid, and that's entirely within quantum mechanics. It's certainly there. But in addition to that, people have speculated already in the mid-80s whether there's wave function collapse, meaning that by nature itself and spontaneously things would shrink their wave function. And the assumption would be that they do this, the more massive they are, the more frequently they would do this. And so this model was really constructed by Girardi, Rimini, and Weber, and later generations of theorists to explain the classicality of our world, that we don't see delocalization. And that also constrains a little bit the parameter range, and but still it's a vast parameter range. And essentially, yeah, there's the two parameters that are of interest are the collapse rate, how often does that happen for elementary particles, and how often does that happen for big things, and to what kind of size of wave function. And the claim is that this should be quadratic in mass, and that's why doing these experiments with high mass particles really kind of makes sense. And so based on these LUMI experiments, these interferometer experiments, we can set bounds in collapse radius and collapse rate, which are close, so touching on the values that had been proposed by Adler as reasonable values. That was already including some kind of magnification mechanism, which must not necessarily be there, but at least it has been a prediction that was around for 13 years, and the green curve with our LUMI experiment kind of eliminates half of that, half of the noise level there. And in terms of interferometric tests, that's currently the most sensitive and most stringent test. But I should also say that there's a bunch of very advanced experiments which are non-quantum experiments, which only in quotations prepare very cold particles or very cold cantilevers or very cold atoms and launch them, very cold electron systems, and look for anomalous heating. Because if there's any such collapse, this is an increase of the wave function curvature, and curvature means kinetic energy. You can also see it as a momentum exchange with a classical field without saying what that classical field would be. But there is a momentum kick involved in this wave function collapse, and that would cause anomalous heating. Actually, this would violate energy conservation, but if we're looking for non-standard physics anyway, why not even accept that? So this is kind of the logic behind these collapse models. And there are more stringent tests with non-quantum experiments, so heating, observation of heating experiments, or observation of the absence of X-rays emitted by a block of a solid semiconductor block, which would also start radiating X-ray radiation just because electrons would collapse every now and then, their wave function. So none of these experiments has ever seen any of these effects. So far, there is no indication that this collapse is really correct. But the question is, how far do we have to go to really exclude it permanently? And my current claim is one would need to go to 10 to the 9 mass units. If you asked Gerardi, who passed away a while ago, sadly, so we can't discuss that with him anymore. He once claimed that if you go to 10 to the 9 mass units for a second, he would give up his model. And then when I asked him later, he was ready to go to 10 to the 16 mass units. But at some point, the model simply doesn't make any sense anymore. And to me, it's about 10 to the 9 and 10 to the 10 mass units and seconds coherence rate. But one can also use that same experiments to define another parameter, which was introduced by Stefan Nimrichter and Klaus Hornberger, which they called the quantum macroscopicity. And they try to compare a variety of different experiments, interferometry experiments, but also cantilever experiments, squids, to give them the same measurement parameter to be able to compare them somehow. And for interferometers, at least, it's relatively straightforward. They introduced this mu, the macroscopicity parameter, as the logarithm of 1 over the natural logarithm of the fringe visibility compared to what you theoretically expect as a fringe visibility. That's your fidelity, if you wish. And then it goes like the mass of your particle divided by the electron mass squared and the coherence time. And that kind of makes sense, that measure, if you also want to compare it to non-interferometric experiments. But what does that really mean? So to give a pictorial example, so if we get to a macroscopicity of 14, that's a logarithmic value, this means that this is 10 to the 14 times more sensitive than a thing with 1. And the thing with 1 is if you have an electron with the same fringe visibility as ours for a coherence time of a second. And so being able to get to a macroscopicity of 14 means that this is 10 to the 14 times more macroscopic in that measure compared to an electron interferometer. So if you wanted to get to the same value, you would have to have a coherence time in the electron interferometer of 80 million years. So that's a very long time. And as you can see over the years, since 1980 already, of course, that's retroactively assigned these values. People didn't bother about that before around 2010 or so, 13. But if you compare the measurements retroactively, you see that there's a continuous, almost exponential increase in macroscopicity, and we hope that this will still go on for quite a while. But currently in that measure, and our LUMI experiment is kind of the record holder, hopefully soon to be overrun by and overtaken by other experiments, both in-house and external. So the crosses were neutrons, the squares were atoms, and the green dots were molecules, and the diamond is really our most recent experiment. Okay, now in a certain spirit, this is a Schrodinger cat. Well, you all know what a cat is. Something that is complex and macroscopic, should be in two very clearly distinct states, like being dead and alive. In our case, it's being here and there. I also add to that it should be warm, otherwise it's not a cat. And of course, I add it should have at least one biomolecule, otherwise it's not a cat. That's not an uncontested theory in our community, but it makes that our molecules are the only cats. Okay, so, but in what sense are these cats, and in what sense are they no cats? So these oligoporphyrines are cats because they have 2,000 atoms, they're in a superposition of being here and there. They're even hotter than a living cat. They can be 600 Celsius, where a cat would be dead. And they're relatively big. And they're separated by much more than their own diameter, typically 50 times. So one can write this down as an entangled state, as a mode entangled state, which looks a bit like a GHZ state, with 2,000 atoms flying on the left-hand side and 0 on the other side, and vice versa. People usually don't do this because you cannot extract useful information from that entanglement with vacuum, even though in photonics people have done this around year 2000 also. But just to say, well, this is kind of a cat. What is missing really to make it a proper cat, probably Sacha Roche would always say you need also entanglement with a macroscopic, microscopic, and macroscopic thing. But here, this kind of entanglement is only there in decoherence, so to say. But to make a real cat, you would like to make it also a biological cat. And the molecules that we are superposing already now are as massive as a green fluorescent protein. But it's not green fluorescent protein. So it's not yet a protein. The question is why? And really the answer is because it's so hard to make sources and detectors for these things. And we have been working on this and are working on this. And I will give you only one snapshot, only for 2 slides. It's not yet a protein, it's an amino acid, sorry, it's a polypeptide made up of 15 amino acids. In this specific case, gramicycline A1, which is an antibiotic. You see the chain, how it's composed of the many amino acids. And the typical difficulty is to launch these things. And the way we did it here was to shoot on a coated wheel that was coated with these molecules and with a terawatt per square centimeter of femtosecond laser light. So huge, humongous amount of laser light, but for a very short time. And that launches these molecules, they're entrained in a supersonic argon jet, and then they're cooled immediately, they survive. At least a good fraction of them survives and is then carried into the interferometer. And well, the interferometer in that case is a modification. I don't spend too much time here on the details, but it's again a 3-grating interferometer, only that instead of mechanical gratings, there are 3 ionizing UV gratings, but the same purpose, coherence preparation, diffraction, and interference pattern detection. And as you can see from the red curves and black dots, the experiments, the theory curves, and they fit together. So even for these biological things, there is interference. Now, how can we really scale this up to high masses to either probe this collapse model or maybe then also look for other non-standard things? And so currently we're working on what we call LUMI 2.0. And this is again about an entirely different class of particles. This is about metal clusters, currently hafnium clusters, where you can easily generate up to 2 million mass unit particles, no problem. That could also go to 10 million or 100 million mass units. So you can make size selected, well, first not size selected because they are generated in an aggregation source, but you can post-select them in a quadrupole mass filter. This is not really the standard application in chemistry to go to 1 million mass units with quadrupoles, but you can do it, and we do. We can cool them in a, again, quadrupole buffer gas cell, and then change their charge state using laser light. So that's the idea. We've started setting this up. They're good signals, very intense signals of very massive particles, which can be size selected. And so what's missing, still quite a bit of work, is to combine this kind of source, so the mass selected metal cluster source, with our ionizing interferometer, which will be again a new interferometer really, with frequency doubled green laser lights, continuous green laser light, to make 3 UV gratings, ionizing laser gratings. And for detection, there's a variety of applications, time-of-flight mass spectrometry. You can also absorb them, image them. So there are different techniques. So that's work in progress, and that will hopefully get us to a few 100,000 or million mass units. And that becomes already interesting, as you will see in a minute, for some varieties of dark matter tests, if we can run it for a year continuously. But that's still a bit in the future. Okay, so, but what effects would you expect to see at high mass? And gravity is a big agent, somehow you could say. On the one hand, and that was a suspicion that the group of Serge Reynaud in Paris had a long time ago, that the gravitational wave background could do something. And the idea would be that if you delocalize your particle in this kind of diamond-like interferometer, the different arms would shift their length if a gravitational wave comes by. Of course, that's a very tiny effect. And to be honest, the prediction is for our very, very slow molecules or clusters, I don't expect any sensitivity to gravitational waves. But interestingly, And I forgot to mention that here explicitly. So we thought about that in the context of hydrogen interferometry, and Christian Brandt in Ulm is now pursuing such a project because that could actually become sensitive to gravitational waves. So, but that would be rather at the lightest and fastest possible atom instead of the most massive and slowest possible particle. Then there were ideas that, well, you may have, if the interferometer is ever so slightly tilted, or if it's really tilted by 90 degrees, then there's a gravitational redshift between the bottom and the top part. And with atom interferometry, I'm sure this will be seen very soon. In these atom interferometer fountains with 10-meter flight path and half-meter separation or so, with atomic clocks on them, they will see this. For our particles, that's not relevant, I think. Then there was a hypothesis, and that's still an open hypothesis, whether quantum space-time makes that space-time fluctuate. And if it does so, then the suspicion was, or the prediction was by Charles Wang and Bingham and other people, that these space-time fluctuations would shake the interferometer, and that would become sensitive if the mass is sufficiently big and the de Broglie wavelength is sufficiently small. Now you would say, well, space-time fluctuations are probably at the Planck length, so 10 to the minus 35 meters. But what they suggested is a kind of Brownian diffusion on top of that space-time fluctuation. And so their latest paper of 2006 or 7, I'm not sure if I cited here the latest one, still predicted an effect around 10 to the 6 mass units. I'm not quantum gravity guy enough to check the equations properly, but that's what they said. So that's a motivation to go also to this regime. Then two groups suggested, well, gravity could cause entanglement, but for that you would have to have a superposition of two particles, both in a superposition, so separated by 100 micrometers, and so large spatial superpositions, much larger than anybody can generate at the moment. And with masses, at least in 2017, they predicted 10 to the 14 mass units, so far off what we can do at the moment, but still as a vision. And I think most recently they have scaled the numbers a little bit down so that it becomes more realistic. But so there's an ultimate question. If you really go to high masses, does gravity start to entangle the quantum state? And that's by itself a very reasonable assumption. But before you get there, maybe dark matter comes in. And that is probably of stronger interest to our friends in Mainz, where really the experts are sitting. But there was a prediction by Jasriel and Ita Yarin. Actually, Jasriel started to write about it already in 2013. And then every 2 years he wrote, well, the Vienna experiments should be very sensitive to dark matter. And in the beginning, I was always skeptical. And we had a number of emails exchanged, and we met several times. But I can follow the argument somehow. The question is whether we can become sensitive enough. So that's still an open question, but I can explain the idea in a minute. Spontaneous collapse, we have seen. Gravity-induced collapse is a little bit coupled to the things above. Also in the same ballpark. But all these effects would scale with m squared. So that's all the motivation for going to high masses. So just 3 slides, and I should watch the time and not get too long. That's kind of the outlook and end, but almost. What would dark matter really do? So there's the assumption, there's a local density, whether it's known, there's a local density of dark matter in our galaxy of the order of 0.4 or so giga-electron volts per cubic centimeter. And it's kind of stationary in the halo of our galaxy. And we are kind of traveling through this dark matter cloud. And of course, it's dark because it hardly interacts with anything. So is there any chance to see it? And the suspicion is there could be a dark mediator, a kind of dark boson coupling between this dark matter and some ordinary matter. And if that happens, then you could see something. If there's a collision, so to say, there would be a momentum kick, momentum transaction. And that's very much similar to the ideas of many other dark matter detectors, only that here we wouldn't look for a change in position of a nucleus, which might, because the charge is moving with it, then excite something in the electron shell. but we would really look for a momentum, for displacement, a momentum kick on our interfering particle itself. And so why is matter wave interference possibly suitable to do something? So I'll skip that, because it's sensitive to extremely small momentum transfers. And high mass interference would be useful because the effect would scale quadratically with the number of nuclei with the mass, because of coherent scattering, at least to some upper limit. Probably not to 10 to the 14 mass units, but in the range that we're talking about right now, 100,000 or million mass units, this would still be relevant. So if there's a tiny recoil, why should that destroy, why should that be visible? Because it generates decoherence. Why is there decoherence? Because the de Broglie wavelength of the exchange particle or the dark matter particle is sufficiently small that it can reveal which path in information. Not to me, because I won't detect it, but to nature as such in principle. So if the de Broglie wavelength of the exchange particle or the dark matter particle is shorter than the separation of the two beam paths of the interferometer, even in a near field interferometer, then you get unique which path information, at least in principle, and that would destroy the interference. So a contrast reduction of your interference that depends on something that is related to the dark matter cloud or the motion of Earth and Sun through this dark matter cloud would be an indication that there's a reaction. And so the prediction is, if it's coherent scattering, and that was the point of Jess Riedel, this should scale like n squared, number of nuclei squared, or the mass squared, and therefore you should go to high mass interference. And the high momentum sensitivity is because you can, in principle, if you can cool the particle sufficiently low, you can split the wave function sufficiently wide that this becomes relevant. And so the current idea is that this experiment can become interesting if we get a contrast stability of 0.1 or 1%. So if we can see very small deviations from the ideal contrast, and if the masses in our interferometers of the order of 10 to the 6 mass units. But this is really back of the envelope estimates, so to say, where we would really be happy to talk to the experts how this can really be assessed seriously. And of course, this would require integrating for very long times because the cross sections would be tiny, and the number of particles is relatively moderate. So all this has to be factored in, and I don't dare to present any serious estimate here because that should be treated still together more carefully. So I really have to come to an end, just to say, unless you let me talk for another half hour or so, but I know that most people want to see an end here. So the metal cluster issue is one thing where we are progressing very well. And in parallel, we have also been working on nanoparticle cooling. Silicon particles cavity cooled to not yet the ground state, but it is cavity cooled. And you may have heard there has been tremendous progress also in our neighboring lab with Markus Arndt, where he has seen ground state cooling in a cavity. So one can assume that ground state cooling in a cavity is feasible and will be around in many labs relatively soon. So I will skip that here and rather focus on the very last thing, namely, once you have this in a ground state, what can you do? This is a Gaussian state. The ground state of the trap is a Gaussian state. I don't say it's boring, but it's not yet the cat that you would like to have. So the question is, how can you make a big Schrodinger cat from that? How can you make large momentum transfer beam splitters? And in parallel, since it comes out automatically, how can you prepare number states, two-level systems, and so forth? On a very generic set of particles from electrons, molecules to nanoparticles. And that is something that Wayne Wang was promoting very strongly, where we've written a preprint that is currently being reviewed. Together with Hermann Bartelan, based on Kapitsa-Dirac, inelastic Kapitsa-Dirac scattering and the Kapitsa-Dirac blockade. And the idea would be that you trap a particle in a one-dimensional trap if you only want the splitting later in one dimension. And this is surprisingly simple. even for electrons, for molecules, for nanoparticles anyway, because you can electrons and molecules, you would just collimate in quotations to 10 microradians, which we do anyway, and you're already in the ground state of a trap. They have lateral temperatures of 100 nanokelvin if you collimate them. So that's easy to do. And but you need a trap, which can be provided by dipole forces, tweezers essentially, and for electrons, which are not polarizable, by Kapitsa-Dirac ponderomotive potentials, and for ions the same, and for nanoparticles by dipole forces. And once they're in the trap, energy and momentum have to be conserved. And if you shine in different colors, you get a momentum transfer of that you can tune, and you have to conserve energy energy transfer at the same time. And it so happens that you can choose the momentum or the wavelength of the laser beam such that you can annihilate transition amplitudes in your harmonic oscillator going to beyond a certain state. So you can make that, you climb up the ladder of harmonic oscillators, and it will deterministically end at a certain spot. And that's what we call the Kapitsa-Dirac blockade. It's this interference of scattering amplitudes, which you find when you do the full quantum treatment. And the transition amplitudes are written here. It's all in the Lamb-Dicke regime, and you can provide a relatively high, surprisingly high, at least on paper, momentum transfer to this harmonic oscillator, and the same description for all these systems because it's a generic harmonic oscillator. And the claim is that one should be able, with numbers that seem realistic to us, to get to a momentum transfer of 1000 h/k, which for a nanoparticle of 1 million mass units would already provide 400 nanometer splitting, which would be good enough for all the tests we want to do in about 30 milliseconds fall time. So this would get rid of any large fountain requirements. This could be done more or less in situ. And that is a very promising scheme so far on paper, and so we don't have any experiments yet on that. So to conclude, so far, well, I haven't spoken much about the proteins, which are also at the core of what we're interested in. And they're still on our future roadmap. Metal clusters is really what we're working on, hafnium currently, but also other atoms. It's easy to change. Just change a disk and get to a different material. And they should go up to a megadalton mass unit, and we hope to see interference, well, not this year. Would also be daring to say next year, but soon. Viroids fall into the same category as proteins, not for this testing of non-standard physics, but it's also of interest to us for other reasons. And the silicon nanoparticles are also being tackled right now. So in the mass range of 1 million mass units to 10 million mass units, I think this is where our interface would be to where we can still seriously do interference experiments on the ground instead of space or big fountains, and where we also believe there might be a chance to connect to the dark matter world. But for that, we really have to learn more and talk to you guys more. And with that, I thank you for your attention.
Yeah, thank you very much for this very nice and exciting talk. So the talk is open now for discussion, questions. Yeah.
I mean, you can just unmute yourself and ask the question, or if you want, you can raise your hand and then we moderate that a bit. Or you can type the question in the chat and we can read it. All possible. I would be wondering, I've made some notes.
Yeah.
Oh, it's hard to read without my glasses. I'm just wondering, what are the challenges when you increase the masses? Is it just that, I mean, what's the main technical challenge that you have to address when you just double the mass of the molecule?
So it's mostly, for quite a while, it was mostly on the source side. As long as you can still evaporate things, that's easy, and that was possible for essentially all molecules below 1000 mass units. Even the vitamins where your mother would tell you don't boil your food so long, you can still heat them for 30 minutes at 500 Kelvin, it's okay. As soon as they become bigger, the chances for disintegrating them in your source are extremely high. That's why we're working on, for organic stuff, so for biomolecules, on typical chemistry methods like matrix-assisted laser desorption, on electrosprays, on ways to charge, reduce, and neutralize these things in vacuum. So that is also on trapping and cooling, buffer gas cooling, and other tricks for organic and biological molecules. And then oftentimes we change just the material class. Like if you do prefabricated silicon nanoparticles, that's an entirely different ballpark than generating metal clusters by yourself, so to say. With the silicon nanoparticles, that's what many groups are doing right now. You can launch them by shaking them up a piezo if they're sufficiently big, but if they're small, you can do that. You can try to thermo electrospray them also. For some particles that works, for others that doesn't. So it's a lot about source development. I would say 30–40% of what we're doing is source development, to some extent physical chemistry. And then you also need to detect them, and the variety of different particles has also extremely different detection schemes. With the metal clusters, I have a good feeling right now that that this is scalable in the sense that we see really all particles from single hafnium atoms up to, well, it stops at 10 million that we can detect them, 10 million mass units, because our detectors are made for that. But I'm sure there's also 100 million or 1 billion mass units. So that is really fully scalable. In that case, you only would have to adapt your mass spectrometers. But I see in the audience, like Ferdinand has been working on quadrupole traps for his lifetime. And you only have to adapt the frequencies or the rod diameters of your quadrupoles to select then a suitable mass range. In terms of interferometry, we're kind of converging now onto a solution that we hope is scalable also. So already starting with OTIMA, this optical time domain interferometer with 3 UV gratings. The concept was right, but the lasers that we were using there, they're still a pain in the neck. These were fluorine lasers. So we are now working or trying to work on systems where we can use CW lasers that can still be pulsed if needed, but high power CW lasers where a larger class of particles can interact with. And 266 nanometers is what ionizes a number of metals. Actually, I think it was 30 or so different, 34, I forgot, different metals that we could tackle possibly. So there's a wide variety of different things. Also, if you're interested in equivalence principle tests where you would like to maybe change the material to compare if they fall the same way or so, that should be relatively easy with that sputter source and with optical gratings, ionization gratings.
I have a question.
Thanks.
May I ask one?
Sure.
How do you want to, for instance, suppress these kind of collisional dephasing, especially if you want to use the buffer gas cooling methods?
Yeah, it's a lot of differential pumping. So you need buffer gas at some point because there's no laser cooling of metal clusters, at least. Well, we can think about it, but there's good laser cooling of dielectric particles. But you need buffer gas at one point, but then every pinhole further, you can reduce the pressure by a factor of 1,000 roughly. So after 3–4 differential pumping stages, you can get to 10 to the minus 12. But if you need to maintain that over a fountain of 10 meters, this is a cost factor, and I would have to apply for money. Well, I need to apply for money anyways, always, but this would be big money. And so we are searching for methods where we don't need these long lengths, where the beam splitting can be done faster, larger beam splitting, still coherent. And yeah, that first has to be demonstrated. But pressure is a big issue. So in particular, if people are talking about 10 to the 14 mass units, this requires a crazy low pressure. If you want 10 to the 14 mass units and 100 micrometer separation, everything that scatters will have rich path information. Even a mosquito that flies in, which you don't have, huh? But it's big enough that really things would fit in between. And so that is extremely demanding. That's why currently on my promise list is only 10 to the 6, 10 to the 7 mass units, which doesn't include that you would see interesting quantum delocalization effects also from 10 to the 9 or 10, but typically only with much smaller separation, few nanometer separation or so, where individual collisions are not so detrimental. If you make it only, if you separate the wave function only by a few picometers, it's still a superposition, less interesting superposition maybe. But then collisional decoherence is not even an issue because there's no rich path information taken away by the nitrogen molecules. Or you need very many to get diffusion. So,
yeah, Markus, thank you very much for the great talk. I have a question about charged particle interferometers. Is that interesting? What kind of application do you see there?
oh, yes.
Perhaps also ionize your particles before they go through the slits or so, that you mimic some, we know the Coulomb interaction is really the same like the gravitational interaction, except it is much larger. So it would be a wonderful thing to mimic the gravitational decoherence somehow in an analog experiment with charged particles.
Yeah.
And there, I also have the question whether this is not perhaps this is even done already by chance, that somebody actually, if you have two ions in neighboring potential wells, and then I think you do this by chance and test all the time an analog experiment of what this paper was about.
Yeah, that's an interesting point. So first of all, I would really love one day to do an experiment with you on ion interferometry, because you're a much better experiment on ions than we are. So as you know, I have always been skeptical because there's a very strong coupling to external electric fields, electric field noise. But with purely optical gratings, I think it can be done in principle. The challenge there is we need absorptive gratings for our kind of near field interferometer scheme, unless you really prepare extreme transverse coherence already from the start, which with your cooling techniques for atomic ions, maybe you can do that. For larger particles, I'm not sure. Yeah, but light grating interferometry is certainly the way to go. And the second, well, is it really the same to have Coulomb forces or gravity? Well, to some extent, yes, it's the same 1/r potential. We believe it's a massless exchange particle, photon or graviton, if there's any graviton at all. And so there are many similarities, but on the other hand, gravity is kind of a bit weirder because gravity is intimately linked to space-time, and space-time is what's really, you have the derivative by time and by space in the Schrodinger equation, also in the Dirac equation. And so this part of gravity is built into the equation, and it's not for charged particles. So I'm not sure if it's really the same. This argument came up many times, and I'm not entirely sure, but it would be interesting to be able to do ion interferometry. And I know only that with electrons it works well. For 500 electron volt energy, it starts to become difficult with material gratings. With light grating, Hermann Bartlein has done nice work with 500 electron volts. There's a lot of decoherence, and well, there was recently, wasn't there a month ago, a Fisher's letter on ion interferometry over very, very short distances. But I forgot what particle that was, in terbium ion maybe. But I have to look this up again. But what people were proposing was to test the 1/r square law behavior of Coulomb forces, if you can do this. So definitely, if one could do ion interferometry, would be interesting. So if you do it, you can certainly make an impact.
Yeah, maybe as a comment to the dark matter search that we do, and you might be doing. I mean, like so we are looking mostly for really ultralight bosons, right? So ultralight means micro electron volt, nano electron volt, pico electron volt, and below, right? So I think there's at 1 electron volt of dark matter particles, they have to be bosons, because otherwise you can't get the density that we observe. Now, for us, the dark matter is basically a classical background field that oscillates, and it's a coherent oscillator with a coherent width that we all know. So the question for you would be, what oscillating fields would your system be sensitive to? Like, how is it with oscillating magnetic field, oscillating electric field, and those kind of things? What happens to your contrast, or what could be an observable?
Yeah, that is an interesting point. So we never looked into these ultralight dark matter particles. So the predictions for us were always between a few electron volts up to mega electron volts, because the higher mass range is kind of excluded anyway. So that was always thinking about this kick kind of interaction. Now, really a macroscopic field, a boson field, I have to think about it. I don't have a clear answer, but we should definitely consider that, yes.
But what happens if you have, like, I mean, you probably have it as some noise, like background magnetic fields or something like this. Do they affect your experiment at all? Do you have to take care of them? Do you have to shield magnetic noise, for example?
Currently, we don't, because most of these molecules that we were working with were kind of in the singlet state, were non-magnetic to some degree. There was some nuclear magnetism, but that's small. So far we didn't need to shield anything. But actually, I'm concerned that, for instance, if you think about dielectric nanoparticles, they can be charge reduced and maybe even neutralized, but some of them may have trapped charges and be neutral because they have a dipole moment. And then electric fields are a severe problem. And that is something that has not been sufficiently discussed in the community, I would say. And it's not proper decoherence, but it will, so if there are fields from, like if you shake your magnetic field from the outside, you would say this is only phase averaging or phase noise, but it does the same thing. It's bad for the contrast. And now if there's a dark matter field coming by, it may be able to do similar things. I do not have any gut feeling how serious that is. So what intensities you would have to have. I really have to understand dark matter better than I do. So we should definitely talk more.
Thanks.
Any further questions or comments?
Well, maybe a comment about this this Debye-Waller blockade thing.
Kapitza-Dirac, yeah.
Or Kapitza-Dirac, well, but it's the same. You have basically, you stop at these nodes of the wave function.
Yeah, exactly. Yeah, exactly.
You can go to higher. So we made, there are several variations of this, which have been already observed experimentally. So there are trapping states for microwave quantum electrodynamic experiments, was proposed, I think the first time by Herbert Walther in the setting of so-called trapping states. And then you can also ask Christian Roos, who did experiments on this. I think they never got published, but we did this and it is really interesting. You can prepare pretty high Fock states in this way by just making the sideband pulse such that you are stopped at the zero crossing of this Gaussian polynomials. And the equation which you have in the transparency is exactly the one from the Vineland Bible, Old Testament book for. So that is really a long-standing thing, and it works. Yeah, it really works. However, if you have a little bit of different power fluctuations also, then you are spilling over the border.
Yeah,
That is the problem there typically. And you can improve the scheme by kicking it from the other side back then, see? You are going to run against the wall, you make some and you're spilling over. But then you start and say, now I'm going from the other side, I'm kicking it back against another wall. So if you interleave, kicking out, kicking in, kicking out, kicking in, that is even better. Yeah. So maybe that's an improvement of the scheme. I don't know.
Yeah. Okay. Yeah. But
at least it works for ion wave packets in this way much better as compared to this, because a tiny bit of intensity of pulse length instability kills the scheme, because then you circle over the sphere once and then does the 2 pi or whatever and over. Yeah.
Yes. Thanks. Yes.
I like it.
Okay. If there are no further questions or comments, then let's thank again Professor Markus Arndt for this nice talk. Before closing, I would like to announce the next talk. This will be then on the January 7th by Professor Antoine Roues, talking about many body physics with arrays of individual atoms and optical dipoles. And also I would like to remind the people that are still here on the theory colloque at 4 p.m. later on. So this will be then about entanglement dynamics in hybrid quantum circuits by Matthew Fisher from University of Santa Barbara. So please join this as well. All right. Now I would like to close our seminar. Wish you a joyful holiday session and a good start to the next year, 2021, hopefully without a lot of restrictions. Like here, please stay healthy.